Okay, next we're going to go ahead and do the next section, Unit 1.3, difference of squares and perfect square trinomials. These are both really very easy as long as you recognize what you've got. So let's start with just the difference of squares. Okay, important thing to understand, the word difference mathematically means, in this particular instance, subtraction. So this is going to be when you have two terms. So not a trinomial, not four terms, but two terms. Here's term one, here's term two. You have two terms, and between the terms, it has to be subtraction. If it's addition, then this difference of squares does not work. Okay. So the second thing, so that's the difference. What's a square? What do we mean by square? We're talking about perfect squares. Okay, so numbers that are perfect squares are 1, because why? Because 1 squared is 1. 4 is a perfect square. Why? Because it's 2 squared. 9 is a perfect square. Why? Because it's 3 squared, and so forth. So 1, 4, 9, 16, 25, 36, 49, and so forth are all perfect square numbers. So you got to recognize our perfect squares and understand what the square root is. So for example, when you see 49, you understand that, oh, that's 7 squared. The square root of 49 is a 7, and that's going to be the important thing that you extract. So again, difference, subtraction of perfect squares. Well, what makes a variable a perfect square? Well, any variable with an even exponent is a perfect square. Why? Because it can be rewritten, in this case, as x times x. The implied exponent are ones, and when you're multiplying variables with exponents, you add the exponents. So that's a perfect square. The square root is x. Example, x to the fourth is a perfect square. Why? Because it can be written as x squared times x squared. The same number is being multiplied twice. X to the sixth is x cubed times x cubed. Why? Again, because we add those exponents. This equals x to the sixth. But an odd exponent cannot be a perfect square because I cannot write identical exponents that add up to be 5. Okay. So the key thing here is just understanding that you are looking at a perfect or a difference of perfect squares. Okay, so how do we do this? Okay, so first you identify the expression is in fact the difference of squares. And you're always going to remove a greatest common factor if there is one. It may not look like it at first, but ultimately it may be a difference of squares. So it must be subtraction, both terms, everything must be perfect squares. If it is, then you're just going to apply a very simple formula. You're going to have two binomials, one with a plus, one with a minus, and the first terms of both is the square root of that first term. And the second term, the b, is the square root of the second term. So for example, if you wanted to factor x squared minus 9, you go, okay, it's a binomial. Both are perfect squares, right? And so therefore, the square root of x squared is what? X, and the square root of 9 is 3 squared, is a 3. And so it fits the pattern. And so it's going to be first terms will be the x, second terms will be the 3's, and there's a plus and a minus in between. If I multiplied that out, if I employed that FOIL, I'm going to get x squared minus 9. The middle term drops off because it'll be a plus 3x and a minus 3x that adds to 0. Okay, so this is very, very, very easy. You just got to make sure that you recognize it and know what to do. So for example, 25y squared minus 49. Well, the first term is a perfect square. Why? Because 25y squared can be written as 5y squared, and 49, of course, is a perfect square, 7 squared. So therefore, you apply the formula to this, and it'd be a plus or minus the square roots for the first term and the square roots for the second term. Okay? 49, or excuse me, 4x squared minus 81. Difference of perfect squares. Square root of 4x squared is going to be 2x. The square root of 81 is going to be 9. And so therefore, it's going to be 2x plus 9, 2x minus 9, plus and minus the square roots. Okay, so you can see very easy. You can pause it for a second, but it'll take you no time to solve these particular problems because they're all differences of perfect squares. So go ahead and do that. Okay, y minus 8, y plus 8, because 64 is a perfect square, as is y squared. 9a squared minus 1 is going to be 3a plus 1, 3a minus 1. The order doesn't matter, the plus or minus. And then 49m squared minus 36, they're all perfect squares. So 7m minus 6, 7m plus 6. Okay. Now, where you might get yourself into trouble, let me just give you an example of something. So let's say we had 3x squared minus 75. Okay, so if you took a look at this, you might go, not it's two terms, but they're not perfect squares. And you may go, and if something can't be factored, because not everything factors, you would say, oh, it's prime. In other words, it cannot be factored further. But what you did is you missed the first step in all factoring, removing the greatest common factor. So both of these contain a 3. So if I factor out a 3, I end up with this. And if you remember my kind of joke from the last class about the 11th commandment, right? You got to factor until you cannot factor any further. Well, this binomial that resulted when you remove the greatest common factor is, in fact, a difference of perfect squares, right? So you would have to continue the factoring. And x squared minus 25, well, the square root of x squared is x. The square root of 25 is 5. And as always, we put a plus and minus in between. So that would be the full factorization. So if it's two terms and it does not look like differences of squares, there's a good chance you may have to factor out a greatest common factor. Okay? There's another one there. I'm not going to go through it. These should be pretty obvious. Okay, now we're going to look at perfect square trinomials. Now, these are to look at are not going to be quite as obvious. There's a little bit of work done, but if you don't catch this, then you're probably going to try to factor it using the AC method, which is going to be much more difficult. So what you want to do is when you have a trinomial and you want to and you want to try to use the AC method, before you do that, you want to check and see if it is a perfect square trinomial and then factor it that way. So let's take a look at what constitutes a perfect square trinomial. Okay, so there should be two patterns. They're all going to be positive, or there might be this negative sign. But what you're going to see straight off is that the first term and the last term are both going to be perfect squares, just like we did before. But there's going to be a middle term, and that middle term, if it computes to be 2ab, then it's in fact going to be a perfect square trinomial. And the pattern will be, if it does meet it, you're going to have the square root of the first term, the square root of the last term, and the sign in front of the second term, in this case plus, squared. Or if it's a minus sign in front of the second term, it'll be a minus. Okay, so perfect square first term, perfect square third term. The middle term is you multiply 2 times the square root of the first term times the square root of the last term. And if they multiply to be the middle term, then it is a perfect square trinomial, and you can immediately write the answer. So let's look at an example. Now, here's a problem here we'll use as an example that you probably wouldn't use perfect square trinomial, but this will illustrate the point. So we notice that the first term is perfect square, the last term is a perfect square. So the question is this a perfect square trinomial? So the test, the check that we're going to perform on the middle term, it's going to be 2 times the square root of the first term, which is an x, times the square root of the last term, which is a 3. And if I multiply all this together, I get 6x. Well, 6x is the middle term. So therefore, this is a perfect square trinomial. Okay, it fits the pattern. And so the factorization will be the square root of the first term, the square root of the last term, and the sign in front of the second term, the quantity squared. Okay. Well, if you factored this using the method we learned before, you'd say, well, I'm looking for factors of 9 that add to 6. So you would have come up with 3 and 3. So you would have said, okay, fine, that's x plus 3 times x plus 3. And this is probably the way you would have done it. Well, these are identical factors. And so we use exponents as shorthand to indicate that we're multiplying exactly the same thing twice. So in shorthand, you would say this is really just x plus 3 squared. Okay. So again, you probably wouldn't apply this to this example because it would be easy just to factor it the normal way. Okay. But let's try a problem that's a little bit more difficult. Now notice that if you took a look at this problem, if you were given this, and you notice there's a 4 in front of the squared term, you go, well, I'd like to factor that out if I can. Well, you can't. 4 is not a factor of 25. So you may be inclined to try the AC method. And if you did, you could factor it, but it's going to be a little bit more work. And so what you should try to do before employing the AC method is just do a quick check. Is this a perfect square trinomial? So you look at the first term and the last term, and you go, well, these are both perfect squares, right? So A, the square root of 4y squared is going to be 2y, and then the square root of 25, the B in the pattern is going to be 5. Okay, so both are perfect squares. And so now we got to test, is the middle term going to be correct? Remember, it's going to be 2 times the square root of the first term times the square root of the second term. So it's going to be 2 times 2y times 5, which when you multiply, I already did the 2y, made it 10y. It does multiply to be 20y, which is the middle term. Okay, so the pattern fits. It's really quick to check it. And then what do? You write the first term is going to be the square root of the first term. The second term is going to be the square root of the last term. And the sign will be whatever in front of the second term squared. Much quicker, much easier. Possible to do AC method, but you're going to do a lot more work. And then take a look at this one. Okay, well, if you did the AC method, you would do 36 times 49. You're going to get a gigantic number. And then you got to try and find factors that add up to 84. That would be a little bit of a nightmare. So before you ever launch into the AC method, is you want to go ahead and do a quick check and go, is it possible that this is a perfect square trinomial? Well, what's the square root of 36s squared is 6s. Square root of 49 is 7. If I multiply these two and then multiply by 2, well, 7 times 6 is 42 times s is 42s. 42 times 2 is 84. That is the middle term. So this passes the test for a perfect square trinomial. So what do? I go ahead and write that first term, the square root of it, you can see right below it. Here is the 7, and this gets a plus sign because there's a plus sign right there, quantity squared. Okay. Again, here's another one. Perfect square first term. 1 is a perfect square because it's 1 times 1. So does it meet the requirements to be a perfect square trinomial? So multiply out the square roots. 10x is the square root of the first term. 1 is the square root of the second term. So 10x times 1 is 10x. Then you always multiply those by 2. And what do you get? You get 20x. That is the middle term. So now you can very quickly write the factorization. Okay. Pretty easy. So what I'd like you to do is go ahead and do the homework for your differences of squares and perfect square trinomials. Okay? Good luck with that.